Hello and welcome to another video. In this video we're going to be working on count subarrays where the max element appears at least k times. And in this problem you're given an array nums and a positive integer k, and you want to return the number of subarrays where the maximum element appears at least k times. And a subarray is a contiguous sequence of elements, so right away contiguous, look for sliding window as I said earlier. So in these examples they show you kind of like what are the subarrays, but let's look into a custom one. So what we want to be able to do ideally is figure out some condition to make this in linear time. So what you could do is for an end index, like the way to do it in brute force would be like for an end index. Now you could do the worst one, but you know, a rough optimization is like for an end index, let's say this one. We need to find the start index where the number of the biggest element is k. So if k is like 2 in this case, our biggest element. So first we can just like go through an array and get the biggest element, which is 3. So if we can get the count of where k is, or like the smallest subarray where k is 2, which is here. So given this end index, we can figure out like, okay, where does this left thing have to be for the count of the biggest element to be exactly k. Then we know that everything bigger than this will be a valid subarray. So this is a valid subarray, this is a valid subarray, and so on. So we can just figure out like, okay, this is at index 1. That means that everything from here to the start will be valid. So because that's at index 1, it's 2 valid subarrays. Same thing for like, given this end index, we can just count backwards, and we want to get to the location where the count of the biggest element is 2, which is going to be here. And that means that for given this end index, right? And because when you do subarrays, you can either do by like start or end index or some other thing. So we can just say like given an n index, what's the smallest subarray we can make where this is true. And so this is this in this case. So that means that this is valid, this is valid, this is valid, this is valid, this is valid. And that's like an n squared brute force. So we can do that for every single end index. But we can bring it down into a sliding window as well now that we have that condition. And so let's walk through that solution. So what we're going to do is we're going to start at the beginning. We're going to keep track of how many 3s we have. And then anytime we have more than enough, or anytime we have like k, we can just shrink it into the smallest window we can have. So let's walk through that. So here we have no 3s, so we can just keep going. Here we have 1 3, so 1. And so we have 1, so it's not enough, so we just want to keep going. Because like if we have only 1 total, we can't shrink it. So here we have 2. So, or we don't have 2. This is a number we don't care about. We only care about the biggest element, so we just keep going. Now here we have 2 3s. So we basically want to shrink it up until, so our count here is 2. So we want to shrink it up until this left thing is on a 3, right? And the count is 2, because that's the smallest it can be. Because if the count is 2 and this is right here, that means if we make it any smaller, this will be invalid. So given this end index, we have 2, and the left is here. And now that we know the left is here, like I said, the number of subarrays is just how many indices are there with this one and before, right? So like this is valid, this is valid. So there's 2, and we can do that in of 1, so we can have a result. That'll be 2. And let's just see for the case. So of the first 5 elements, we should get 6, so we'll look at that, and then we'll keep going. So we keep going. So now we have... and from here on in, like there's always going to be subarrays, right? Because here, like here we have enough 3s, so every index past this, even if it's not a 3, there will always be subarrays. So let's go back. So here we have 3 3s. So what we want to do is we want to shrink it up until we have 2 3s, and the left index is on a 3. So that's going to be right here. Because that means that if we make it any more, then this will be invalid. Like as soon as we make the left go further, it'll be invalid. So now we have 2 3s again. And how many subarrays are there given this end index that are valid? Well, it's just whatever the index of the left is plus 1. So this is valid, this is valid, this is valid, this is valid. So there are 4. So 6. And now if we look from 0 to 4, the answer is 6. So let's keep going. So here, the count is 2, but we can't shrink it anymore. So how many subarrays are there with this end index that work? So once again, the count of left plus 1, right? So like this is valid, this is valid, this is valid, this is valid. So we add 4 again, so 10. Then we have a count of 3 now. So we do the same thing. We shrink it as much as possible. So we're going to shrink it up until the count is 2 and the left is on a 3, which is right over here. And we will update our count. And how many subarrays are there that are valid? There's 5, right? Because this is the smallest one. That means everything past this is valid. So 1, 2, 3, 4, 5. So 5, so we have 15. And finally, this is a 0, so we can't shrink it. So how many subarrays are there that end with this that are valid? 5 again, so 20. So that's kind of like small tricks to using sliding window. You basically just figure out a condition that you can do this in linear time. And when you're counting subarrays, you can either do this by start or end index, make it the smallest one possible or the biggest one possible or something, and know that like everything from here to a certain point is valid, and then you can just count that into a 1. So if we know like, okay, this is the smallest one that's valid given this end index, anything bigger than this where we stretch this out is also valid, and we can just get all those into a 1. And so that's what we're going to code up. So essentially, once again, to remember what we did. So we get the biggest element just by looping through, getting that. Then anytime the count is 2 or more, we will shrink it to the smallest valid subarray possible, and then we know everything bigger than that is valid, so we can just get that in of1. Okay, so let's do that. So first we're going to get the biggest element possible. I think everything in here is positive, so we can just say like int biggest equals 0, and we can just loop through and do it. So num and nums biggest. I believe you can't do a max of a list in Java, so you have to do it this way. Someone can confirm me if I'm wrong. Num and biggest. Okay, now that we have that, the same kind of things for our template. So we have a result, we have a count. All we need is how many of the biggest number we have, so that's just an integer, and we have a left. So same thing as yesterday, except now instead of a hash map, we have a count, and these are all ints. So int, and int. Now we have our sliding window, so we're going to loop from every element from the start to the end, same as yesterday exactly. So int right equals 0, right is less than num's length. And then what we need to do is we need to check for every element, is it the biggest element? So if num's right equals biggest element, we need to increment our count. So now what we need to do is we need to say while our count is greater than or equal to k, then we need to shrink our subarray. So we need to shrink it until it is until it's equal to k and the element on the left is that number. So we can say while count is greater than k or count equals k and num's left does not equal the biggest number. And then we can just put this in parentheses. So let's do that. So now we just say the same thing. So if num's left now equals biggest, then we decrement our count. Okay, and we can just increment left over here. Yeah, so that part is fine. And then what we need to do is, so after this loop, like we don't necessarily have valid subarrays yet, so we can just have a check here. So we can just say like if count equals biggest, or not biggest, count equals k, that means that we have valid subarrays here. And we should be at the index of the smallest one possible. This should be, no, this is fine. Yeah, so if the count equals k, then we have valid subarrays, and our left is on the smallest index possible, or like the smallest subarray possible. So anything past that will work. So we can just say result plus equals left plus 1, right? So going back to our drawing, like if this is the smallest one possible, then there's 5, because if we're on 4, it's 4, 3, 2, 1, 0. So same thing. Yeah. And then, so we have that, and I think that should be it. Now we just return. There's like another way to write it that's a little bit cleaner, but it's a little bit less intuitive, so I just went with this one. Then we return result. And we should hopefully have the right answer. Let's see. Oh yeah, I forgot one thing. So the number can be pretty big, and they want you to return a long. So you just this needs to be a long, and this maybe needs to be a long as well. Actually, this count doesn't need to be a long, and it'll fit in an in, but whatever. Yeah, so this just needs to be a long. So we had an overflow. Some things you never have to worry about in Python. That's one of them. Okay. Yeah, so that's going to be it for that one. So let's do the time. So we found a sliding window solution. So first thing, we get our biggest number, O of n, looping through O of n. So O of n, space. So now the space usually for sliding window just comes down to like, what are you keeping track of? And in this case, all we kept track of was a count. Before we had a hash map in yesterday's problem, but this is just a count. So all constant time, or all constant space, so O of 1. And yeah, this one is a little bit trickier to come up with the condition for the sliding window than the last one, but it's kind of the same idea. You want to either figure out like what's the biggest or smallest or something possible, and then you need to know that like, okay, everything past this is a valid subarray, and then using that you can get the number of subarrays with a given end index or a start index depending on the problem in O of 1. So that's kind of the idea. Definitely a little bit harder than the one yesterday, but hopefully this was helpful. And if it was, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.